4.5 billion years ago, Mars wasn't the frozen desert we see today. It had something Earth still has, something that made rivers flow and rain fall from thick clouds. Then, over hundreds of millions of years, something stripped away 99% of that atmosphere, leaving behind a world where the air pressure is less than 1% of Earth's. NASA's MAVEN spacecraft has finally revealed what happened, and the answer is written in the solar wind itself. This isn't just ancient history. It's happening right now, this very second, as you listen to these words. Let's break down what happened to Mars' atmosphere and why Earth didn't suffer the same fate. The evidence is everywhere on Mars' surface. Valley networks carved by flowing water snake across ancient highlands. Dried river deltas fan out where streams once emptied into crater lakes. Rounded pebbles tell us water flowed long enough to smooth their edges. But here's the critical detail. Liquid water cannot exist on Mars today. The atmospheric pressure is so low that water immediately boils away, even at freezing temperatures. For ancient Mars to have had liquid water on its surface for millions of years, it needed an atmosphere at least 20 to 30 times thicker than what exists today. Some climate models suggest it might have been even thicker than Earth's current atmosphere. This wasn't just a thin envelope of gas. This was a protective blanket dense enough to trap heat, regulate temperature, and create a weather system with clouds, rain, and seasonal cycles. But Mars had a vulnerability that would prove catastrophic. Deep beneath its surface, the planet's core was cooling. Around 4 billion years ago, Mars' liquid iron core solidified, and when it did, the planet's magnetic field collapsed. This wasn't a gradual weakening. Geological evidence from Martian meteorites suggests the magnetic field shut down relatively quickly in geological terms, perhaps within a few 100 million years. Earth's magnetic field extends 60,000 kilometers into space, creating an invisible shield called the magnetosphere that deflects the solar wind around our planet. Mars had something similar once. Magnetic striping in ancient Martian crust proves this. You can still see the fossil record of that dead magnetic field frozen in rocks from Mars' first few 100 million years. But when the core solidified, that protection vanished. Mars stood naked before the solar wind, and the stripping process began. The solar wind is not a gentle breeze. It's a supersonic stream of charged particles, mainly electrons and protons, blasting outward from the sun at speeds between 300 and 800 kilometers per second. Every second, the sun loses about 1 million tons of material through the solar wind. This plasma carries the sun's magnetic field with it, creating what scientists call the interplanetary magnetic field. When this magnetized plasma slams into a planet without a magnetic shield, something violent happens. The solar wind's magnetic field connects directly with the planet's ionosphere, the upper layer of atmosphere where solar radiation has ionized the gas molecules. This connection creates what's called magnetic field draping. The solar wind literally wraps around the planet, and in doing so, it picks up ionized atmospheric particles and carries them away into space. MAVEN has measured this process in real time. The spacecraft detected ion plumes streaming away from Mars' atmosphere, being ripped away by magnetic field interactions with the solar wind. MAVEN launched in November 2013 and entered Mars orbit in September 2014 with one primary mission: understand how Mars lost its atmosphere. The spacecraft carries 8 scientific instruments designed to measure everything from escaping atmospheric particles to the solar wind's interaction with Mars' magnetic environment. What MAVEN discovered was shocking. Mars is currently losing atmosphere at a rate of about 100 grams per second under normal solar conditions. That's roughly equivalent to a quarter-pound burger floating away into space every single second. But that's just the baseline. When a coronal mass ejection from the Sun hits Mars, the atmospheric loss rate increases by a factor of 10 to 20. During these solar storms, Mars can lose several kilograms of atmosphere per second. MAVEN measured one such event in March 2015, when a powerful solar storm compressed Mars' magnetosphere and dramatically increased the escape rate. The spacecraft's instruments revealed that atmospheric loss occurs through several mechanisms. Pickup ion escape, where solar wind magnetic fields grab ionized particles. Sputtering, where energetic solar wind particles literally knock atmospheric molecules into space. And photochemical escape, where solar ultraviolet radiation breaks apart molecules, giving atoms enough energy to reach escape velocity.
Now here's where it gets interesting.
If Mars is losing 100 grams per second today, how long would it take to strip away an entire thick atmosphere? Let's do the math. 100 grams per second equals about 3.1 million kilograms per year. That sounds like a lot, but Mars's current atmosphere has a total mass of about 25 trillion kilograms. At today's loss rate, it would take 8 billion years to lose even the thin atmosphere Mars has now. But Mars lost most of its atmosphere in far less time than that. The answer lies in the ancient Sun. 4 billion years ago, our Sun was much more active than it is today. Young stars rotate faster and have more powerful magnetic fields, which means more intense solar wind and far more frequent coronal mass ejections. Studies of young Sun-like stars suggest that the early solar wind could have been 100 to 1,000 times more intense than today's solar wind. If we apply those ratios to atmospheric loss rates, Mars could have been losing tens to hundreds of kilograms per second during its early history. At that rate, stripping away most of a thick atmosphere becomes possible within 500 million to 1 billion years. That matches exactly what the geological record shows. But there's a fascinating twist to this story. Mars' atmosphere didn't disappear uniformly across the planet. The southern highlands of Mars contain something remarkable: crustal magnetic anomalies, which are regions of ancient rock that retain strong magnetic fields from when Mars' dynamo was still active. These magnetic anomalies act as miniature magnetic shields. The Mars Global Surveyor discovered these features and found that above these magnetically shielded regions, the atmosphere is actually thicker and atmospheric loss rates are lower. It's like Mars is wearing patches of armor in certain spots. The strongest anomalies are found in Terra Cimmeria and Terra Serenum in the southern highlands. In these regions, the ancient crustal magnetism is actually strong enough to deflect some of the solar wind, creating mini magnetospheres. This tells us something important. If Mars had maintained its global magnetic field, it likely would have retained its atmosphere. The presence of these localized shields proves the protective effect of magnetic fields. The atmospheric loss wasn't just about gases disappearing. It triggered a cascade of consequences that transformed Mars completely. As the atmosphere thinned, surface pressure dropped. As pressure dropped, liquid water became unstable. The rivers stopped flowing first. Then, the lakes began to evaporate. Some water soaked into the ground and froze in the subsurface as permafrost. Some water was locked up in the polar ice caps. But much of it was lost to space along with the atmosphere. Here's how. Water molecules in the upper atmosphere get broken apart by solar ultraviolet radiation in a process called photodissociation. The water molecule splits into hydrogen and oxygen. Hydrogen is so light that it easily escapes Mars' weak gravity. The oxygen either escapes as well or reacts with surface rocks, creating the iron oxides that give Mars its distinctive red color. MAVEN has detected hydrogen escaping from Mars' atmosphere right now. The spacecraft measured hydrogen atoms streaming away from the planet at a rate that confirms water is still being lost today. Over billions of years, this process has removed an ocean's worth of water from Mars. Studies suggest ancient Mars may have held as much water as Earth's Arctic Ocean. Most of that water is gone, lost to space or locked in subsurface ice. The story gets even more dramatic when we look at solar storms. Mars' thin atmosphere is already vulnerable, but during coronal mass ejections, the planet faces something far worse. When a CME hits Mars, it compresses the planet's induced magnetosphere, pushing it closer to the surface. This compression allows the solar wind to penetrate deeper into the atmosphere, reaching denser regions where more particles can be stripped away. MAVEN observed this firsthand during the March 2015 solar storm event. The spacecraft measured the atmospheric loss, increasing by a factor of 10 during the peak of the storm. But here's the critical insight. 4 billion years ago, when the young sun was firing off coronal mass ejections hundreds of times more frequently than today, Mars was being hit by these atmospheric stripping events constantly. Instead of a few major solar storms per year, Mars might have experienced several per week or even per day during the early solar system. Each storm would have ripped away massive amounts of atmosphere in just hours or days. This wasn't a gradual erosion. This was episodic, catastrophic stripping. The combination of intense baseline solar wind plus frequent devastating solar storms created perfect conditions for rapid atmospheric loss. Understanding what happened to Mars' atmosphere isn't just about ancient history. It has profound implications for our search for life in the universe and for any future human presence on Mars. First, the habitable window. Mars likely had surface conditions suitable for life for perhaps 500 million to 1 billion years after its formation. That's actually a substantial amount of time. On Earth, life appeared within the first billion years, so Mars had enough time for life to potentially emerge. But as the atmosphere thinned, the surface became increasingly hostile. Any life that may have developed would have been driven underground or into protected niches. This is why astrobiologists are so interested in Mars' subsurface. If life ever existed on Mars, it might still exist deep underground where liquid water could persist in aquifers insulated from the surface conditions. Second, the human exploration challenge. Any future Mars base will need to account for ongoing atmospheric loss. While the current loss rate is slow on human timescales, radiation and solar storm events remain serious hazards. The lack of a magnetic field means the Martian surface is exposed to harmful cosmic radiation and solar particle events. Future Mars colonists will need substantial shielding and likely underground habitats to protect against this radiation environment. Mars' atmospheric catastrophe is one of the most dramatic transformation stories in our solar system. What began as a world with flowing rivers and a protective atmosphere became a frozen desert through the slow but relentless stripping power of the solar wind. The magnetic shield failure left Mars defenseless against space weather that continues to erode its atmosphere even today. This discovery doesn't just explain Mars' past. It shapes how we search for life beyond Earth and how we plan to explore and potentially inhabit the red planet ourselves. MAVEN continues to orbit Mars, measuring the ongoing atmospheric escape and teaching us about planetary evolution across the cosmos. Subscribe to Orbital Atlas for more deep dives into the mysteries of space exploration. We're just getting started uncovering what's out there.